Tert butyl hydroperoxide is a very versatile oxidizing agent, similar to hydrogen peroxide, with the added advantage that it's soluble in pretty much all organic solvents. It's got a fearsome reputation for being extremely hazardous, and in situations other than fires, this is largely unjustified. I'll explain why at the end of the video, but for now let's just focus on making it. The reason I'm making it is to carry out low temperature decarboxylation without heavy metals, a method that was first documented in the 1950s, used in some notable syntheses in the 1960s, so both Eaton's and Pettit's cubane syntheses, and then largely forgotten about, probably because the more flexible Barton decarboxylation was developed in 1983. But that reaction needs exotic and gimmicky reagents that I'm not prepared to pay through the nose for, so I'm falling back on the older method. The first reported synthesis was conducted by Miles and Harris in 1938. The method involved combining T-butyl alcohol with aqueous hydrogen peroxide and using a large amount of desiccant and multiple distillations over metaphosphoric acid to remove the water. They noted it was by far the most stable of the simple alcohol hydroperoxides, apart from its tendency to explode in an open flame. Whether they meant deflagration or detonation is not clear from the context. A more practical and efficient synthesis was conducted by Meshcheryakov, Batyov and Matveeva in 1955. Their method involved bubbling isobutylene gas into 63% sulfuric acid and oxidizing the resultant T-butyl sulfate with hydrogen peroxide. The whole reaction was conducted between about 0 and 10 degrees C. T-butyl alcohol can also be used in place of isobutylene, and that's the basis of the method I'll be demonstrating, since I can't easily get hold of isobutylene cylinders. The key difference is that the reaction time is much longer because T-butyl alcohol is less reactive than isobutylene. The reagents used were deionized water, 40 grams, azeotropic sulfuric acid, 40 grams of that, T-butyl alcohol, 16.4 grams, 24% hydrogen peroxide, or 30 grams of that. Sharp-eyed viewers will have noticed that the stuff I called T-butyl alcohol is called 2-methyl-propan-2-ol on the label. As Billy Joel didn't quite sing, you can call it 2-methyl-propan-2-ol, but it's always 2-butyl alcohol to me. Despite the label claiming 98% purity, it contains some water. Pure T-butyl alcohol freezes around 25 degrees, but this stuff stays very much liquid in my Soliterne lab, where, thanks to the damp course, the ambient temperature is a pretty constant 15 to 18 degrees, regardless of the time of year. The density is also higher than that of pure T-butyl alcohol, consistent with the water content of around 10%, meaning that it's most likely azeotropic. The first step was diluting sulfuric acid from around 98% to supplying to 50%. This was done slowly and carefully in an ice bath because the reaction between water and sulfuric acid is very exothermic, and letting it heat up too much at this point wastes time when you have to cool it down later. Because of this, the process was very slow, but it's the most practical way of creating a solution like this, since doing it the other way around would have resulted in the water boiling the moment it hit the acid. The next part was adding the 90% of T-butyl alcohol to the diluted sulfuric acid, again in an ice bath to slow down or stop the elimination reaction to isobutylene. This could be done more quickly as there was nowhere near as much water present in the alcohol. After that, hydrogen peroxide was added, again slowly, and the mixture was naturally warmed to room temperature. The entire process took 2.5 hours from start to finish. The mixture was left to mix for 3 days, during which it separated into 2 phases as per Meshcheryakov. 2 layers were separated using a separating funnel. The most obvious sign a reaction had taken place was a change in smell. T-butyl alcohol is one of the more pleasant smelling organic solvents, being fresh and minty, while this stuff had a similar but harsher smell. The easiest way to gauge purity is by measuring the density, since T-butyl alcohol and T-butyl hydroperoxide respectively have densities of 0.78 and 0.9 grams per milliliter. The yield was 9.68 grams, or 55% with respect to T-butyl alcohol. The density as measured was little under 0.9 grams per mil, indicating a high purity, which was confirmed by its energetic properties, which are reduced when it's diluted in a solvent. The yield could likely have been improved by using more concentrated sulfuric acid or hydrogen peroxide, which reduces the amount of water in the reaction mixture, as water is a byproduct of the reaction. Reducing the amount already present is likely to result in more product, plus it makes separation of the product more efficient. Now, let's have a look at those energetic properties. The reason T-butyl hydroperoxide has such a fearsome reputation is because the US National Fire Protection Agency has given it the highest hazard rating in all three categories: toxicity, flammability and instability. Its auto-ignition temperature is a mere 70 degrees, which means that a large quantity of it would be extremely hazardous in a fire. To put it into perspective, the clips you just saw were all filmed using 1 or 2 drops of material. Imagine what would happen if a fire was to hit a 25 kilo drum of this stuff. However, that does not mean that it's similarly hazardous under normal conditions. It's been known for over 80 years and it's widely used in industry and academia. If it really were that hazardous in general, there would be a ton of anecdotal evidence about its hazards, as there is with hydrofluoric acid, hydrogen cyanide, white phosphorus and other extremely hazardous substances. But there isn't. For an alternative source, let's consult the European Chemicals Agency, which requires producers and importers of over 1 tonne per year in the EU to provide safety data and publishes the results on its website free for anyone to view. The catch is that the data can be wildly variable, but unless it's a very obscure compound, it's usually a lot of data and it's easy to determine which physical hazards are consistently proven across all studies. These are summarised on the screen. If you want to have a good read of them, now's the time to use the pause button. Assuming you weigh around 50 kilograms or 8 stone, well, that's 110 pounds in freedom units, you'd need to ingest around 28 grams or absorb 28 grams of it through the skin to receive an acute lethal dose. Breathing in a dose of 42 milligrams per litre of air continuously over multiple days will eventually kill you. None of these scenarios are likely if it's handled properly. As far as instability goes, it is an organic peroxide, but organic peroxides were not created equal. There are 7 categories of organic peroxide from A to G, with category A being the type that detonates if you look at it funny, and category G being the type that might detonate if you confine it and heat it aggressively with a blowtorch. The REACH regulation contains a flowchart that allows for easy categorisation. The category F rating is based on its properties as a 70 to 80% aqueous solution, which is the most common form in which it's commercially available, but the properties of the pure substance I've observed put it into category C. This is comparable to benzoyl peroxide, which is a common anti-acne medication. In overall terms of hazards, other than the fire-related ones, it's a jack of all trades and a master of none. The label needs more badges than a punk rocker's jacket, but provided you take sufficient care to keep it away from heat, flames or sparks, it's not outstandingly nasty. So in summary, T-butyl hydroperoxide is not something to be taken lightly, but under normal circumstances it's not the flaming liquid death it's often claimed to be. I hope you enjoyed this TED Talk. Thank you for watching.